Hello everyone. Today we'll go over the applications of logarithmic functions. Just a reminder, this is the last lesson of the unit and in the meantime the last new lesson of the whole course. Logarithmic functions are widely used in everyday life to describe quantities that are either very large or very small. We have chosen logarithmic functions to do this because they do a great job at describing very big or very small numbers. And the explanation for it has its roots in the very meaning of the word logarithm. Remember, logarithm means exponent, and a small change in the value of the exponent in an exponential number can bring out huge changes in the value of the exponential number itself. So take as an example the numbers 2 to the power of 10 and 2 to the power of 11. A small change in the exponent by only 1 unit can make the exponential number 2 to the 10 twice as big as before. Now, similar to this, we can take a look at the numbers 2 to the power negative 10 and 2 to the power negative 11. A decrease by 1 unit in the exponent can make the exponential number twice as small. One of the uses of logarithmic functions is when we're measuring the intensity of an earthquake, so how strong or how weak an earthquake is. Now, if I ever asked you, how do we measure earthquakes? I'm pretty sure you'll quickly say, oh, we use the Richter scale. That's one of the uses, at least. Now, by the way, Richter was an American seismologist and physicist. He lived from 1900 to until 1985, I think, and he dedicated his life to physics and science, and he is most well known for the development of this very special formula that we're going to take a look at together right now. Okay, so Richter decided that it is very difficult to measure how strong an earthquake is. You cannot just base it on the stories that people tell you, so he wanted to put a number to it. And just like we do with any quantity that we measure, take as an example 1 meter. So what is 1 meter? Well, people decided that 1 meter will be this long. That was a decision made. That was 1 unit. And everything that was twice as big, then it would be 2 meters. Everything that was half as the 1 meter, it would be half a meter, right? So the same thing or the same system or reasoning was used with measuring earthquakes, but in a different kind of domain of mathematics in here. They decided that the intensity of the earthquake that you can barely notice or you can barely feel is intensity I0. Okay, and anything compared to this would be intensity I. So if you divide I by I0, then you are going to get again some exponential number, and you take only the log of the exponential number in order to tell what the scale of the earthquake is. So by the way, this is a Richter's formula, m equals log of I over I0. It will make more sense as we go over the examples. Now, on the Richter scale, the energy of the earthquake increases by powers of 10. How do we know this? Well, think about it this way. We have the log in here. We don't see the number on the base. That means the number of the base is 10. So, for example, an earthquake below magnitude 4 usually would cause no damage, but earthquakes below 2 cannot even be felt. And an earthquake with magnitude 6 is strong, and 7 or higher can cause major damages. That's just to get a picture of the magnitude of the earthquake, so how to feel it and how to understand it. So we're going to take an example here. An earthquake of magnitude 7.5 on Richter scale struck Guatemala on February 4th, 1976, and it killed 23,000 people. On October 2nd, 1993, an earthquake of magnitude 6.4 killed 20,000 people in Maharashtra, India. We have to compare the intensities of the two earthquakes. So here I'm going to build two charts actually. So here goes Guatemala. And here goes Maharashtra. Okay. And I'm going to say that the earthquake in Guatemala was 7.5. So when we say 7.5, that would be the magnitude of it. And the earthquake in Maharashtra was 6.4. I'm going to call one of the earthquakes M1 and the other one M2. Now remember that the number of casualties of people that die in an earthquake cannot measure how strong an earthquake is, obviously, because you can tell that the earthquakes in here have different magnitudes. But when it comes to the number of people that lost their lives in here, it's kind of very close to each other, okay? So that's why we use the Richter scale. So anyway, so we're going to move on to rereading the problem and trying to make more sense of what we're given and what we're asked to find. We want to compare the intensities of the two earthquakes. And remember that when we use the word compare, means that we need to find the values I2 over I1 or vice versa. So I1 over I2. Oops. Okay, so how do we go around this? Now, all we know, or what we do, is we start off with the formula we know about the intensity of the earthquake or magnitude of the earthquake. So we're going to say that in Guatemala, M1 would be the log of I1 over I0. And in Maharashtra, M2 must be the log of I2 over I0. Remember, we want to compare intensities, so we need to solve for I1, we need to solve for I2, and then find the ratio, either I2 over I1 or I1 over I2, it doesn't really matter. So for M1, we'll have 7.5 here, equals log with base 10, obviously, I over I0. And for M2, we have 6.4 equals log of I2 over I0. So we are trying to solve for I1. I1 is inside the log, which means that we have to use the definition of log in here in order to extract or to gain access to I1. So we're going to say that this base 10 in here raised to the power of 7.5 will give I1 over I0. So we're going to say that again, I1 over I0 equals 10 to the power of 7.5. And that will make I1 equal to I0 times 10 to the power of 7.5. Now don't let the I0 that is unknown in here stop you on the way to solving the problem, because we are comparing quantities in here, so most likely it will simplify somehow. So similar to this, we're going to do the same thing for Maharashtra's earthquake. We're going to say that I2 over I0 equals 10 to the power of 6.4, and that will make I2 equal to I0 times 10 to the power of 6.4. And now if we want to compare the two intensities, then we're going to say that we have something to compare them with. I1 is I0, so I'm going to use this formula here. So I'm going to start with I1, which is I0, 10 to the power of 7.5, divided by I0, 10 to the power of 6.4. So I0 simplifies. 10 to the power of 7.5 divided by 10 to the power of 6.4 equals 10 to the power of 1.1. Okay? And we're going to say that 10 to the power of 1.1 is equal to, here's a calculator, 10 to the power of, okay, so 10 to the power of 1.1 is 12.58, so 12.6 actually. So we'll say that I1 over I2 equals 12.6. Therefore, we're going to say that intensity in the earthquake of Guatemala is 12.6 times stronger. So Guatemala's earthquake is 12.6 times more intense. So notice how with by using the log, or by using the exponent, we were able to describe two quantities that varied largely between each other. Okay, so moving on to another use of logarithms is when we describe sounds. So the loudness of any sound is measured relative to the sound of a threshold of hearing. The sounds at this level are softest and can still be heard, and the formula that we use for loudness is L equals 10 log of I over I0. So it's a formula very similar actually to the magnitude, but we also have a coefficient of 10 in front of it. I is the intensity of the sound being measured. I0 is the intensity of the sound of the threshold of hearing. Just like for intensity, we had I0, the intensity of an earthquake that you could barely feel, right? And everything was compared to that. Same with the intensity of the sound. And L is the loudness, is measured in decibels. So the unit measurement in here is called decibel. It is actually named after Alexander Bell, which, by the way, is Canadian, as you know, and dedicated part of his career to discovering or describing the loudness of a sound. Now, the table below is just for out of curiosity, just so we can create an idea of how much a decibel is. So we call 30 decibel a soft whisper. We call a normal conversation 60 decibel, which is twice as intense as a soft whisper. Shouting 80 decibels. Subway 90. Screaming child 100 decibel. You'll experience this one day. Beautiful day. A rock concert 120 decibel. Take a break after attending one. A jet engine 140 decibels. Just don't stay near one. And a space shuttle launch is 180 decibels. Now, exposure to 85 decibels during a 35-hour week will eventually cause damage to most ears. And 85 is between shouting and subway, so you don't want to be near there because the drum bell will damage somehow. And 120 decibel volume is the average rock concert, and it will cause damage in less than half an hour. So the higher the level, the less time it takes for the sound receptor to start dying and permanent hearing damage occurs. So a body has self-healing, competencies, let's say. And about 130 decibels after 75 seconds, you are at risk of suffering permanent damage to your hearing. Okay, great. So we'll take a look at an example. And we have example 2 says the sound is 1,000 times more intense than the sound you can hear. Okay, and what is the measure of its loudness is in decibels. So if I'm asked to find the loudness, I'm going to write the loudness formula because that's the one that will help me solve the problem. And we have 10 log of I over I0. Okay, and we are told that the sound is 100 times as intense as the sound you can hear. This is the sound I can hear, and this will be 1,000 times as intense. So I will say I equals 1,000 times I0. That's the information given. And I want to find out the loudness, which is unknown. So using the loudness formula, we have 10 log of I over I0, and for I, I'm going to write 1,000 I0, and I will leave I0 where it was. Obviously, we can simplify I0 now, and we're going to say that loudness is 10 times the log of 1,000. Remember what is sitting down here at the base of this log is number 10, and we're going to say as a result that loudness is 10 log with base 10 of 10 to the power of 3. These two numbers will beautifully simplify each other, and we'll end up with L equals 10 times 3, right? And that would equal 30. So we're going to say that the loudness would be 30 decibels in this case. Okay, now the next question is for you to try. And I will move on